Okay, today is day one of section 5.5. We're not going to be doing the entirety of section 5.5. We're going to focus on two new sets of formulas. One set is the double angle formulas. That's what's going to be the focus of today's lesson. And the next lesson will be the half angle formulas. And that'll wrap up what we're going to be covering from section 5.5. What we're going to do first is derive where do the double angle formulas come from. Well, they're a direct result of examining a set of formulas we already know, the sum difference formulas. So as a recall, this is our set of sum difference formulas right there. In order to get the double angle formulas, we are going to look at, well, what if u and v are both the same angle? Now, for the types of problems we did in section 5.4, they typically were different angles, but they could have been the same angle. We didn't necessarily treat that as a special case. Now we're going to look at is what if they're the same? Well, what if they're the same and we look at the difference version of each one of these guys? So instead of u and v, we'll make them both the same variable, in this case u. So sine of u minus u is just sine of 0. Cosine of u minus u is cosine of 0. Tangent of u minus u is 0. So there's not much going on here. It's kind of a pointless little exercise here to think about what if we're using the difference formulas with u and v being the same. So as this slide says, not much to see here, folks. Let's move on. All right. Now what we're going to do is the sum version. And we're going to do, on this slide, sine and tangent. Cosine's a little bit more interesting. We're going to examine that on the next slide by itself. So if we take the sine sum formula, let both of those angles be the same. In this case, they chose to use u. It gives us sine u, cosine u, cosine u, sine u. Well, they're the same term. We can add those together. So our double angle formula for sine is sine of 2u is 2 sine u cosine u. All right. For tangent, we're going to take the tangent sum formula. We're going to let both these angles be the same. Again, they chose to use u. Tangent u plus tangent u, 1 minus tangent u, gets us to here after we combine like terms up top and multiply those together. Now, this looks like the bottom may have a Pythagorean identity. It's kind of got that feel to it. So let's just confirm something real quick. We know that 1 plus tangent squared is equal to secant squared. Can that be used in any way to rewrite the bottom? At first glance, it looks like maybe it's a possibility. Well, 1 minus and 1 plus certainly aren't the same thing. If we were to bring this tangent squared over there, if we were to bring the 1 over there, and the secant squared there, no matter what you try, you're not going to get this to be anything that we can use with that. The only thing we could possibly do with this is that's a difference of 2 squares. It could be factored, but that really doesn't do anything for us for what we're looking to accomplish for today. All right. Next, we are going to examine, zoom in a little bit on this. Focus. Okay. What if we examine the cosine sum formula? So we're going to take the cosine sum formula, let these guys both be the same angle, and that gives us cosine u, sine u, sine u. Or in other words, cosine squared minus sine squared. So that's one version of what we could use for the cosine double angle formula. The other thing we could do is to replace that cosine squared with 1 minus sine squared, and that gives us a version that's purely just sines on the right. And we know from different things we've done so far in this chapter, sometimes that's definitely to your advantage, to have a single trig function rather than 2 different trig functions mixed together. The other option is we could take that same version from here that we had here and replace sine squared with 1 minus cosine squared. And when we clean that up, it gets us to here. So we have three different versions for the cosine double angle formula. We could use this one, which is the one that most directly comes from here. Or we could use this version, which is in terms of sine, or use this version, which is in terms of cosine. So the same as it's been for several things we've done in this chapter, we're going to pick the version that makes the most sense with the context of the problem that's around it. All right, so in summary here, we have our sine double angle formula, our tangent double angle formula, and we have three different versions of cosine to choose from. Now, due to the unique circumstances of this school year, I'm not having you guys memorize formulas. In previous years of teaching this class, there would always be some assessment where you'd have to memorize formulas. And one of the things that I would be encouraging students to do is, if you already know the sum difference, you can derive any one of the double angle formulas simply by knowing that in combination with a couple of other basic identities. So I wouldn't want you to be, even if I was asking you to memorize formulas this year, actually memorize all three versions. If you already know the cosine double angle formula, you can get this. And if you know that with your first Pythagorean identity, you can get the other ones. But anyway, for this particular school year, naturally those of you that are taking assessments at home, open book, open note, those of you that will be taking assessments in the classroom will be allowed some kind of reference sheet, and these would be on it. All right, now on to what are we going to do with these guys? So what's going to be happening here is we're going to revisit problems that we've seen in the past in terms of the context, and then how would these new formulas fit in? So for the first example right here, this box up just here just recaps our formulas so we have them as reference. And we're going to look to see how would this play out in a right triangle trig problem. So for this example, we're given a 5, 12, 13 right triangle. That's our angle of interest down there. So given this diagram, what's the sine of twice that angle, cosine of twice that angle, tangent of twice that angle? Well, for sine double angle, there's only one version to choose from. We don't have too many options. We're going to start with 2 sine cosine. We're going to extract that information directly from the picture that we're given. The sine of that angle, 12/13, cosine of that angle, 5/13, and then it just becomes order of operations. Okay, for cosine, we have 3 different versions we can choose from. Since this is simply find the cosine of twice that angle, there really is no advantage whatsoever at all, depending on which one of these you choose. Pick whatever one you want. This slide, it shows the first one. So, cosine squared minus sine squared. Cosine comes from the picture. Sine comes from the picture. Order of operations, express your final answer. Now, for this particular slide, they've asked us to find sine, cosine, and tangent. If we've already found sine, and we've already found cosine, we can simply just divide these two things to get tangent. We don't have to use this formula. If you want to, you can. But it's certainly more efficient if you've already figured out sine of twice the angle and cosine of twice that angle. Here and here, just simply divide them in order to get tangent. All right, second problem solving scenario here. Looking at angles in standard position. So our given is the cosecant of the angle is negative root 26. The radical got chopped off here for some reason. Now recall, this statement alone, when you're talking about angle in standard position, is not enough to locate it in the coordinate plane. They have to give you some other piece of information in terms of what quadrant to draw it in. Okay, given this information, what's the tangent of twice that angle? So, theta being between 3 pi over 2 and 2 pi puts it in the fourth quadrant. So we're boxing it into the closest x-axis, angle to the closest x-axis like we've done many times before. Okay, cosecant of theta is equal to negative root 26. That's the same as sine of theta. is equal to negative 1 over root 26. So I prefer to work with that. So I am going to label this negative 1. That's root 26. So your a squared plus b squared equals c squared. So we got 26 and 1. Subtract them, that's 25. That makes this a 5. We're heading to the right, so it's got to be a positive 5. Now, in contrast to the previous slide, the only thing they're asking us for is the tangent of twice that angle. So it's not efficient to find sine, find cosine, and then divide them. This is a case where we want to actually work off the tangent formula. So 2 tangent u, tangent is going to be negative 1/5. That's the top of the fraction over here. The same tangent that's there gets squared on the bottom. So the negative 1/5 goes there, square it, and now it just becomes order of operations. 2 times negative 1/5, negative 2/5. 1 minus, negative 1/5 quantity squared is 1/25. 1 minus 1/25, 24/25, etc., until we get to a simplified final answer. All right, so we've certainly done right triangle trig, now in the context of double angles. We've done angles in standard position, now using double angles. Next problem solving situation. Equation solving. So for this first example right here, we got 2 cosine of x plus 2 sine, can't read, let's start over again. 2 cosine of x plus sine of 2x equals 0. If that wasn't there, we know how to solve this back from section 5.3. If that 2x, sine 2x in the middle wasn't there, we know how to solve that from section 5.3. The new thing is, well, what happens if they're both in the equation at the same time? Okay, when you see a double angle and a single angle both in the equation at the same time, that's going to be your clue that you want to do a substitution with the double angle, because all of these formulas get you from a double angle to a single angle on the right. Now, to replace sine of 2x, we only have one option: 2 sine x cosine x. Now, once we put that in here, now this becomes a 5.3 equation. We can factor out the 2. We can factor out the cosine. That gets us to here. Set each piece of what we factored equal to 0. And here, solve each equation. That implies all solutions. So we want that 2 pi n flavor at the end. Okay, for these problems, meaning the double angle substitution problems, there is a very low risk of extraneous solutions. This is not one you have to worry about checking the solutions with. You can assume that if you get the answers down here, barring an arithmetic or a trig mistake, they will work. Very low risk of producing extraneous solutions. All right, example number 2 from this slide. Cosine of 2x equals 2 sine squared of x. Again, reminding what we know and what we don't know. If we just had a sine squared in the equation, we can solve that from 5.3. If we just had a cosine of 2x in the equation, we can solve that from 5.3. Both of those mixed in the problem at the same time is no longer a 5.3 equation. Okay, when you have a single angle and a double angle, both in the same problem, that's your clue that you want to replace a double angle with one of these guys. Now, for this particular equation, it's cosine of 2x we're replacing. We have 3 options of what we could replace it with. We want to replace it with the option that makes the most sense in the context of what's around it. If this is in terms of sine, then we want this to be in terms of sine. We've added layers of complication to the problem if we don't choose the correct option. So we're going to replace that cosine of 2x with 1 minus 2 sine squared of x. Now that we're here, we're back in section 5.3. We literally spent a week on solving these types of equations. Okay, whatever strategy applies is what you want to use. Particular to this problem, get this over there, flip the sides, square root both sides. Don't forget, if you introduce a square root, you got to do the plus minus thing. Means we're going to get a solution in every quadrant. We're looking for all solutions instead of just a particular interval, which means we're going to leave them in that 2 pi n form. Okay, also, as a general reminder, when you have solutions that look like this, there is the risk of redundancy. Or it's possible that it could be condensed. I believe both of these guys can be condensed to smaller equations. I think this can come down to one equation, and I believe that could go down to two equations. For the purposes of free response questions on quizzes and tests, the same as it's always been, I'm not going to require you to identify redundancies or condense. Just be aware for checking your answers in the back of the book, and for choosing multiple choice questions, you may have to examine what are the actual angles that are being described here, and then compare them to either the answer in the back of the book or your multiple choice options. All right. Back to an angle in standard position, but this one's going to be a little bit more challenging. Cosine of 2 theta is 4/5. Theta is between 0 and pi over 2. Find the tangent of that angle. All right, so what we have to do here is, if we know a double angle value like this, we're going to have to get to something that's a single angle. So for cosine, we're going to begin with one of those 3 formulas. Okay, we do not want to choose the first one because that's 2 trig functions mixed in the same problem. We want to choose one of those 2. So begin with one of the following cosine double angle formulas that will allow us to solve for a trig function of theta. So it doesn't matter which of these 2 you choose. This one will allow us to solve for sine of theta. This one will allow us to solve for cosine of theta. Okay, the author of this slide decided to use this one here. So we're going to plug in that 4/5. This equation right here, we can solve for sine. We're going to bring over that 1. 4/5 minus 1 is negative 1/5. We're going to divide by negative 2. Negative 1/5 divided by negative 2 is 1/5. We're going to divide by 2. 1/5 divided by 2 is 1/10. And then we can solve for sine by taking the square root of both. Now, initially, we're going to consider the plus or the minus of the root. But since theta is a first quadrant angle, we know sine has to be positive. We're only going to take the positive root. Now, once you know the sine of an angle, and you know what quadrant you're in, now we're back to, like, last chapter, whenever that falls in. You can find any other thing that you want to find. So given the sine is 1 over root 10, we're in the first quadrant. What's the tangent of that angle? So sine would be 1 over root 10. That makes that a 3. Tangent of that angle, 1/3. Now, one thing of interest with this problem is we never know actually what theta is. We know that twice theta is 4/5, and that's enough to tell us what the tangent of theta is without actually knowing the angle. So kind of an interesting problem-solving situation. All right, last connection. Back to graphing. Now, when we were in the graphing unit, you had problems that looked like this, where you were asked to find features of the graph. Typically, it would be something like domain, range, period, amplitude, etc., etc. And because of the structure of this, you didn't necessarily have the tools it took in order to be able to identify it just from the equation itself. For this type here, what we did is you put it into your graphing calculator, you got a picture of the graph, and then from the picture of the graph, you were able to answer some questions. All right, now what we're going to do is use some set of one or more of these guys in order to be able to answer those types of questions without relying upon the graphing calculator. So, first thing we're going to do is look to see what general form does this have. So that's sine cosine. So the one that's sine cosine marries up with that. So we have 10 sine of 4x, cosine of 4x, and what I'm going to do is write that right underneath it. 2 sine of u, cosine of u. I'm going to put this on the right. Sine of 2u. All right. So, how do we handle this? Well, in the formula here, we got a 2 that's a coefficient in front. That's a 10. So to get from there to there, you'd have to multiply by 5. So that means we'd have to multiply this by 5. All right. Here to here means that we're getting from, use the X here, make the variables match. Here to here is multiplying by 4. So whatever this is has to get multiplied by 4. Ooh, I didn't want to fill that in. Shouldn't have done that. That makes that, fell apart all the way around on that. 5 sine makes that 8x. So this function and this function are identical. They're going to produce the same graph. Prior to this particular section, other than observations and looking at a picture on a graphing calculator, we had no way of identifying any features of this graph. Now that we know how to write this to this, now we can identify features. Specifically, they're asking us for period and amplitude. So the period is going to be 2 pi divided by the b term. So the period is pi over 4, and the amplitude will be 5. Absolute value of the a term in front. Now you can confirm that in the graphing calculator. In the interest of time, we're not actually going to be sketching this out. We spent literally weeks graphing sine and cosine. Whatever is appropriate, do it from there. All right. The second one here, 7 cosine squared, x over 8 minus 7 sine squared, x over 8. This has the same basic structure as this. So we want to marry those up. Let's see, let me get a separate piece of paper here. So 7 cosine squared, x over 8, minus 7 sine squared, x over 8. I'm going to write the other form right underneath it. Cosine squared of u minus sine squared of u is equal to cosine of 2u. So, coefficient in front, coefficient in front, coefficient in front. Whatever these are, that's going to be the same thing there. So whatever these are, same thing in front. Okay, here to here, they get doubled. So these guys have to get doubled over there. So now that gets us in a form where we have very predictable rules in terms of features like period, amplitude, etc., etc. So the period for this one is going to be pi divided by 1/4, which is 4 pi. Amplitude is going to be 7. All right. H, that number minus sine squared, looks like that this is going to pair up with the cosine double angle formula. So we have 2, copying the wrong one. 1 minus sine squared u is equal to cosine of 2u. All right, so we got whatever this is, twice that. Whatever this is, twice that. Oops. I messed this up. That's where it was. I was pointing to the wrong one and I copied it wrong. Okay, whatever this is, twice that. Whatever this is, twice that. This matches that. So this has to be the coefficient. All right, whatever this is, twice that. So we have to double that, 20 pi x. So this is our form that we have nice predictable rules for. So the period, did I mess this up? It's 2 pi divided by 1/4. 8 pi. 2 pi divided by 20 pi. So that's going to be 1/10 for the period, and then the amplitude will be 3. All right, tangent. The only thing really going on here is a 2, 1, 2, 1 means there's not going to be any change in the coefficient in front. That's going to stay 1. And then whatever these are, twice that. So if that's pi x, that's going to be 2 pi x. This is the one, tangent for the period divided by the b term. So the period is 1/2. And then amplitude, tangent does not have an amplitude. All right, that is it for this section.